And this week, we're going to introduce electrostatic sensors. So these kinds of sensors are to let the robot know the environment. So such as the force or torque. So it's different from the torque and acceleration here. This is for the joint, and the force and torque sensors here is for the external objects. So basically, it's usually measured as the end effector. And also have the proximity sensor visions. So this is kind of camera, and also have sound, smoke, humidities. So all these kind of sensors is measure the environment. So by this kind of sensor data, the robot can know what environment is surrounded. And the first one is the force torque sensors. So there are many kinds of force torque sensors we are using, but the most simple one is the strain gauge. So this is the indirect information obtained from the measurement of the deformation of an elastic element. So I don't know how many of you have already have the when a force is applied to a beam or a material, the material will bend it. So this is when the force is applied to a material. So if we measure the bending, the deformation of the material, then we can know the force. So this is how the strain gauge is used to. So a strain gauge is used to measure the strength. So it is a type of passive transducer that converts a mechanical displacement into change of resistance. So if the material deforms, you will have the mechanical displacement. And the strain gauge will use its circuit to measure the charge of resistance. So this kind is a resistance strain gauge. So it's most widely used device for measuring strength. So based on the principle, the electrical resistance of a conductor changes when it's subject to a mechanical deformation. And after that, we will introduce how this strain gauge how the strain gauge can measure the strength. So I don't know how many of you have already known this one. It's the Wheatstone bridge. So this is the electrical circuit used to measure an unknown electrical resistance. So here we have a battery, we have a voltage, and to the A and C points, and we have 4 resistors. So you can say it's R1, R2, R3, and R4. And here we all have 2 circuit loop. So inside here, this is the strain gauge reading. So Rx is a known resistor, and R2 and R3 are phase value resistor, and R4 is a variable. So you can see there's a variable error here. And G is a galvanometer. So if we vary the R4, then there's no voltage drop between B and D. Then we will have VB equals to VD, and we can get this one, the Rx. The relationship between the Rx and the other 3 resistor is like this function. So how can this function measure the deformation? So the output delta R, the R of the strain gauge is usually converted to a voltage signal with this Wheatstone bridge. So we can go to the end of the function. So by these 4 resistors, they have a relationship between them. So when Vg is 0, so there is no voltage drop from B and D, the bridge is in a balanced condition. And if we have the 4 variables added to the 4 resistor, so you can see here is R minus delta R, and here is R plus delta R. And here is R plus delta R, and here is R minus delta R. So this kind of Wisdom bridge is called a 4 variable amps. So the voltage VD, through the calculations, we can have see it is the delta R divided by R times the Vs. So when the resistor, the value is changed, then we can use this one to measure the change of the voltage. You mean?
These slides are they uploaded to media because of that's the final.
I think this week we haven't uploaded yet, but we can upload them in a break. Or you want it uploaded now, or?
No, I was just asking when you're going to upload. Just next week then, or?
Maybe just after the class.
Okay,
Yeah.
That's fine.
This with the Wisdom bridge will be only for introductions. So it's only lets you to know how this kind of sensors, the working principle. So you know, you guys do not need to like really know what are the calculations, and we won't see anything like this during any exams. So basically, the first 2 lecture, the sensors and actuator, is only for the introductions. So this is to let you to know the working principle for all the sensors and all the actuators. So when you want to build a robotic system, you will know what kind of sensors you want to choose, and what's the actuator you want to choose to build your robotic systems. And starting from next week, we will move to our main lectures for the robotics. So starting from the next week, we'll introduce all the transformation metrics. This is the fundamental mathematical modeling for the robotics. So this is a bin-type load cell. So applied load produced by a moment. So you can see here the P is applied forces here. So you have moment over. You will produce a moment at the bin. So the moment is equal to Px, and where x is the gauge location. So this is the x. And the m is like this one is the inertial, and this is the y. So the y is h divided 2. So this is just for information. If you want to calculate what is the deformation and what is the moment of the strain gauge you will measures. And we will have the 4 resistors. So those produce a moment which cause equally and opposite strains, such as epsilon 1 is equal to minus epsilon 2, and is equal to epsilon 3 and minus epsilon 4. So this one will equals. And this is another one. So as a result, the response of the strain gauge is, you can see here is using the formula for the Wisdom bridge. So it's delta R minus R. So it's SG times the epsilon. And the voltage output of a Wisdom bridge with 4 identical active gauge in the push-pull arrangement. So this is a push-pull arrangement. So we can measure the output voltage. So this is the input voltage. So the output voltage can be similar like this function. So this is the lower P. So by here, the sensitivity, the S is the V output and divided by the load. So this is the sensitivity of this sensor. So from this, we can, by measuring the output voltage, we can know the load P, the value of P. So this is the photo of the strain gauge fixed on the robot leg. So this 7 strain gauge is glued to a flexible aluminum beam. So you can see this is a aluminum beam. And it measures the local curvature in direct bending during the motions. And it can also use for measure the joint torque. So you can see a strain gauge is mounted to a sense the axial deformations. You can see here will be a flexible coupling, and it's connected to variable gear, and here is the joint axis. So if there is any external force applied on the link 3, this one will move the joints, and the variable gear will rotate, and you will pull the flexible coupling. So through here, measuring the rotation, we will know what is the external force applied on the link 3. So the force source sensor in the robot wrist is a device typically located between the last robot link and its end effector. So top and bottom plates are mechanical connected by a number of deformation elements. So if we want to use the strain gauge, we need to use the deformable elements, because the strain gauge is measuring the mechanical deformation values and transfer into a resistant value. So whenever, if you want to attach a strain gauge on it, you need to know that this is a deformable element. If you attach this kind of strain gauge on a rigid body, then you cannot get any feedbacks. So since the complete decouple of these measurements is hard to obtain, so there are greater than 6 such deformable elements. So through the design, we can decouple all the degree of freedoms through sensors. So like this kind of, if we place a sensor here, then we can measure the external force applied by this joint axis. But this is not decoupled in the 6 degree of freedom we know in our environment. And we can see something like this. So if we attach any factor on this sensor, you can see this is a sensor, and here is deformable elements. So through this kind of hand sensor, this will decouple all the degree of freedoms. So there are 4 deformable elements. You can see here are 4 deformable elements, and 2 pairs of strain gauge are mounted on opposite side of each element. So there are 8 pairs. And 2 gauge of each pairs are placed adjacent to the same Wheatstone bridge. So usually we will see like this kind of force torque sensors is mounted in the flange of the robot. And so these are the typical flange to measure the end effector force or torque. And whenever we have sensors, we need to do the calibrations. So like this one is all the calibration metrics. So it will have to transform the outputs of the Wheatstone bridge. So this all 8 are the outputs. We can see here we have the 8 pairs of Wheatstone bridge. And this is the output of the 8 sensors. And through the calibration matrix, we can get the force or the torque of the 60 growth rhythms. So here is the force torque measured in the frame attached to the sensors. So what is this kind of applications? So we can see this is a robot, and here is the end effector. So between the end effector and the robot, the frame, here we can implement a force sensor. So the force sensors will measure, like this one is measuring the torque. So if we want to attach a reducer part onto a motor, we need to measure the force in this z-axis, and also we want to measure the torque in the z-axis rotation. And also we can have this kind of force sensors here with the end effector using the polishing tools. So this is the workpiece. So if this tool touching the workpiece, you will generate a force, and also you will measure, because this one is force, you will measure the force and the torque. So you'll know what is the force is pressing on the workpiece. Another application of this kind of sensor is the RCC. It's the remote center of compliance. So it's placed on the wrist so as to introduce a passive compliance to a robot infector in response to a static force and moment applied to environment at the contact area. So you can see here have like several compliance beams. So if we want to do a pack and hold task, so this is a pack, so this is one hole. So if we want to place this pack into this hole, so here it touches the wall of the hole. So it will generate force upward, and then through this remote sensor compliance mechanism, you will measure the force and the torque is produced by the objects and the environment. So you will slide into the hole. So this mechanical construction yields a decoupled or linear motion response to the contact occurs at or near the RCC point. So you can see this one is a linear motion, and this is the rotation motion. And we can see this is the RCC by ATI Industrial Automations. So here are the pin. So here are the slides. So your objects through this kind of RCC frames, then we can have the compliance to slide into the pin. So nowadays we're using the robot learning or the control algorithms. So this is a kind of RCC end effector. And through the learning process, because you will learn the force, you can measure the force and the torque when the peg is touching the hole. And through the learning, then you can learn how to do this task. So this kind of mechanism is not only they have mechanical compliance, and it also can measure the torque and the force when the egg vector holding the object touching the environment. So we come to another sensor. So this is a proximity or distance sensors. So it's measure the distance. So there are several kind of proximity sensors. So by measuring by the infrared, so this is a light source, usually using the LED. So emitting ray beams. So this is their frequency, and it's their length, and which is then captured by a receiver after reflection on the objects. So here, if you can see, you'll have the LED. So here we have a red light. So it will have red light from here to the object's surface, and this is the resistor to capture the lights back to this sensor. So by calculating the time of the light travels, then we can convert it into the length. So it receives intensity is related to distance. And narrow emitting receiving angles used only indoors. And reflecting varies with object color. So this kind of sensor is, you'll know that this kind of sensors is very, very sensitive to the surface, materials, or color of the objects. So if you want to use this kind of infrared, or use like a metal or something will have the scattered light, then maybe you cannot measure very, very the good results. So the typical sensitivity range is 4 to 30 meters, or thereby 1 to 50 centimeters. And the another kind of is using the ultrasound. So use of sound wave. So the last one is use the infrared, is using the red light. So here is using the sound wave. And also have the propagation and reflections. So it's also shooting the sound wave and hitting the objects and reflected by and captured by a sensor. So the distance is proportional to the time of flight along the sensor object sensor path. So you can see this is a typical beam pattern of the sound wave. And today, for our particle exercise, we are using the ultrasound sensors. So, like this one is the navigation with ultrasound sensors. If you want to build a navigation robots or a walking robots or like also locomotions, then you need to know what is the obstacle and all the walls of the environment. So through the ultrasound sensors, you can measure the objects, the distance of the objects from your robot, and you can map the environment. So the next one is using laser. So the laser scanner is two-dimensional scan of the environment with a radial field of infrared laser beam. So time between the transmission and reception is directly proportional to the distance of the objects. So all the working principle of these three kinds of sensors are the same. So only difference is like using the sound wave or the infrared or the lights. So you need to depend on what is the objects you want to detect. So like the surface or the color of the objects, and you can decide what is the sensor is most suitable for you to use. And then we come to the actuators. So we have already introduced that a robot is made up by legs and joints, and we will mount a lot of sensors inside a robotic systems, and usually the actuators is mounted in the joints. So if you see the actuator joints, then they will have some actuators inside these joints. So the definition of an actuator is a mechanical device for moving or controlling a mechanisms or systems. So it takes energy and converts into some kind of motions. So the energy is maybe by air, electric current, or liquid. So we'll introduce this kind of actuators in the following page. So the frequently used as a mechanism to introduce a frequent motions. So these are common actuators in robotics. I think the most common one is the electric motors. And some you will see the hydraulic actuators is using the liquid as the energy. And this one is the soft pneumatic actuators. So this is using the air. You can see this one is the soft pneumatic actuators. So this is a deformation, the soft materials with deformable elements. So if we insert the air inside this kind of actuators, the air pressure will push the materials and cause it to deform. And when it deforms, then it's or bending, then you will have the motion. So this is the soft pneumatic actuators. And also there are some interesting actuators. So when you want to build a robot, you need to decide what kind of actuators you want to use. So like dielectric supernova actuators, or thermal, magnetic motors, ultrasonic motors, or piezoelectric motors. So if we want to build very tiny or small robots, maybe these kind of motors you can use. So first, we'll introduce the electrical motors. So an electrical motor is an electric machine that converts electrical energy into mechanical energy. So I think everybody knows the DC, AC, and stepper motors. So most electric motors operate through the interaction between the magnetic field and the current to generate force. So we introduce what the difference between these three kinds of motors. So the first one is a DC motor. This motor is an electric motor that runs on direct currents. So there typically have two types of DC motors, the brush or brushless DC motors. The brushed DC motors generate torque directly from the DC power supply to a motor by using internal commutations, stationary magnets, and we'll have the figure after that. And on the other hand, a brushless DC motor uses a rotating permanent magnet or soft magnetic core in the rotor and stationary electrical magnets on the motor housing. So here the housing is using the stationary. So a brush DC motor, this is the figure of the brush DC motor. So you can see here have the permanent magnets, and here we'll have the electrical current pass through here, and we'll generate, and we'll turn by the magnetic force field here. So the main components is there's a armature mounted on the bearings. So this is the armature. And you have two stationary magnetic field. And you will have a commutator. So this is the commutator. So commutator. And we'll have a brush. So this is the brush. And let's see how it works. So when the electric current passes through the core, this is the electric current pass through, then so we will push by the magnetic field, then we will produce a torque, and this will have to turn. So the magnetic force, the force is equal to This is the current times the L and times the field, E. So act perpendicular to the false wire and the magnetic field. So if we don't have the commutator, so this one will be rotating to here and backward, here to backward. So if we have a commutator, so it can rotate continuously. So for the first type, when the core is powered, a magnetic field is generated around the armature. The left side of the armature is pushed away from the left magnet. So you can see here is pushed away from the left magnet. So the armature continue to rotate. So you can see it's rotated to the perpendicular degree, the configurations. So when the armature becomes horizontal, aligned, the commutator reverses the direction of the current. So this commutator is used to, you can see from here, if this one is rotates around, then here, for the first half loop, the current is to here and to the core here. If it rotates another way, for another half round, the current is from here to here. This one is rotates halfway, so it can pass through here and back to the battery. So through this kind of mechanisms, it can change the flow of the current. So that's the motor can continuous rotating. So the process then can be repeated. And the advantages of a brushed DC motor is low inertial cost, high reliability, and very simple to control. But the disadvantages of a brushed DC motor have high maintenance and low lifespan. So because you know that the armature is, there is changing between the armature and the core here. So we have some worn-outs, so we have low lifespan. And the maintenance involves regular replacement of the brush and the spring which carry the electric currents. And we come to the brushless DC motors. So a typical brushless DC motor uses a rotating permanent magnet in the rotor and a stationary electrical current magnet on the motor housing. So you can see here, unlike the brush DC motors, the brushless DC motors have two kinds of magnet. One is the permanent magnet, and another one is using the electrical magnet. So the design is simpler than that of brush motor because it eliminates the complication of transferring power from the outside of the motor to the spinning rotor. So the advantage of the brushless motors is long lifespan, so little or no maintenance, and very high efficiency. But because of the initial cost, because we need to have the two kinds of magnet, so the initial cost is higher than the DC motors, and more complicated motor speed for the controllers. So to sum up, this is the DC motor, both the brush and brushless. So the DC motors provide excellent speed control for acceleration and deceleration, and very, very easy to understand the design. So it's simple, cheap, compared to other kind of motor. And the disadvantage of these motors is the brush is high maintenance. So the next one is the AC motor. So the AC motor is driven by an alternating current. So it commonly consists of two basic parts. an outside stationary stator, which having a coil supply to alternating the currents to produce a rotating magnetic field, and an inside rotor attached to the output shift that is given by a torque or rotating field. So this is a figure of the AC motor. So the basic parts is the rotor and the stator. You can see this is the stator, and inside is the rotor. And here you can see more. This is the stator, and here is the rotor. So the outer frame is the outer body of the motor, so it protects the inner part of the machine. So this is the outer frame, and this one is the stator. It's built by a high-grade silicon seal, carry the alternating magnetic field, and the stator winding has 3 phases of winding. So for the AC motors, it's low cost and speed variations and very low maintenance operations. But for the disadvantages, it's inability to operate at low speed and very poor positioning control and limited speed to the frequency supply. So because we know that the AC motors is driven by the alternating current, so the current is changing the phase, changing the phase, the speed. So this is by the changing the phase, you will determine the speed of AC motor. So you have a limited speed. So for DC and AC motors, so DC motors are usually seen in applications where motor speed are need to be external controlled, and AC motor work best in the application where power performance is sort of extended period of time. So usually if we see all the robots motors are used the DC motors. We very seldom see using the AC motors. The AC motor is usually used in the other kind of machines that will operate just running 2 times. And the stepper motors. So today we also, in the practical section, we also use the stepper motors, but a very basic one. So it's brushless and it's synchronous electric motors that can be divided by full rotation into a large number of steps. So the motor position can be controlled precisely without any feedback mechanisms, as long as motor is carefully sized to the applications. So this is like the last week we introduced the absolute encoder. So through the stepper motors, when we design these motors, all the position that already designed into this kind of motor. You can see from this video. So this is a typical motors we see in our robots. So usually in the robotics, but in the robots we're using the stepper motors. But some robots we use the brushless with a very high precision encoder. Because after we design this type of motors, the precision is already designed. So this kind of motor can only rotate 1.8 degrees per step. So this is a variable reluctance. So I think you have seen this in the video. So it has a software multi-tube rotor with one stator. So the stator incorporates a large number of very small field holes and deploys around the circumfaces. And each post piece is fabricated with several teeth. Step angle is related to both the number of stator teeth and the rotor teeth. And this is a graph for the pull-in and pull-out torque of the motor. So this is very important when you want to choose the stepper motors you want to use. So the pull-in torque is the maximum torque against which a motor will start and give a pulse rate and reach synchronism without losing a step. So you can see this is the pull-in torque, the line here, the graph here. And this is the pulling rate. And here is the speed of the motor, and here is the torque. So this one is the maximum pulling rate. It's over here. So it depends on the speed you want the motor to drive. So this is the maximum torque you can use to start this motor. So if you want to use this kind of stepper motors, you need to calculate what is the torque you will need to produce when you start. And for the pull-out torque, it's the maximum torque which can be applied to a motor running at a given stepping rate without losing synchronisms. So if the motor already is running, and this is the maximum torque, so it will decrease when the speed is increasing. So when you are choosing a stepper motors, you need to decide what is the running speed of your motor. So you can map the torque you needed. This is the maximum torque this motor can drive the objects. So through this through this graph, you'll see you'll know whether this stepper motors is suitable for your application. So the next, we come to the hydraulic actuator. So the hydraulic actuator uses the power of pressurized fluid. So this is the mechanical energy is converted into the hydraulic energy. And the hydraulic system can be controlled almost as accurate as electrical motors. I think this is the part I think many people don't know. So we'll have a break.